In the second part of the walkthrough video, we prove the correctness of the sample algorithm we saw in the first part of the walkthrough video. Proof techniques are not limited in this course. In other words, feel free to use any proof technique you are most comfortable with to prove an algorithm. In this scenario, we proved the algorithm from the first part of the video correctly outputs all possible ordering with direct proof and 3 lemmas. Lemma 1, each element in the upper list is an ordering. Lemma 2, every ordering in the upper list is distinct. And lemma 3, the upper list has a size of n factorial for all n greater than or equal to 1, where n is the input size. Proving these 3 lemmas satisfies the theorem due to the nature of permutation, where it generates n factorial distinct combinations of the input list. Here's a sample grading rubric breakdown for the proof idea and the homework assignments. Getting L5 means that we get full score. L4 is a 5% reduction due to a very small mistake. L3 is 20% reduction due to a mistake. L2 is usually half the points. L1 is 1/4 the points. L0 is always no points. Note that this is just a sample rubric. The grading scale might differ depending on the assignment you're working on. This is a sample full score proof idea for lemma 1. We'll use proof and induction to show that every element in the upper list has an ordering. Starting off by proving the base case of n equals 1, the exact element will be returned. The inductive hypothesis will then be developed when n equals k, every element in the upper list has an ordering. Moving forward to the inductive step, this algorithm utilizes the for loop to traverse through every element in the input list, while removing the current node before hitting the recursion. Concatenation of the current element will be made after the recursion to concatenate the current element with the output of the recursion. This is a valid ordering on a list of size k by the inductive hypothesis. Therefore, with proof by induction, lemma 1 holds. Here's a sample L3 version of the proof idea for lemma 1. Similar to the L5 version of the proof idea, but it does not use anything specific about the algorithm other than that it traverses through every element in the input list using for loop. To get L5, a necessary condition is that you explicitly point out which specific part of the algorithm statement you're going to use to prove its correctness. This is a sample L2 or L1 version of the proof idea for lemma 1. Compared to L5 or L3, the inductive set of this version has barely any detail. The reason for the reduction will be does not state explicitly the effect of removing the current element. Does not state explicitly the effect of the for loop iteration. However, this does not get you L0 because it still contains some correct ideas such as utilizing the nature of for loop as a justification of the correctness of the algorithm. Moving on to lemma 2. This is a sample L5 proof idea for lemma 2. We'll use proof by induction on n to show that every ordering in the output list is distinct. Starting off by proving the base case of n equals 1, only one element will be removed. Then an inductive hypothesis will be developed. When n equals k, every element in the output list will be distinct. Moving to the inductive step, this algorithm uses a for loop traversing through every k plus 1 element, meaning that every current element will be distinct. For the same recursive call, the extensions are distinct by the inductive hypothesis. Therefore, with proof by induction, lemma 2 will be valid. This is a sample L3 version of the proof idea for lemma 2. Compared to L5, this version did not apply the inductive hypothesis. It only states that this algorithm uses a for loop traversing through every k plus 1 element, meaning that every current element will be distinct. In other words, no element will be processed more than once. The reason for the reduction is does not extend the idea beyond the nature of for loop, using an inductive hypothesis. This is the L2 or L1 version of the proof idea for lemma 2, most likely an L1. The inductive step of this version misses the majority of the ideas and provides a vague argument. For example, you can't directly tell the relationship between the highlighted part and the algorithm. However, some points are rewarded due to the stating correct ideas, like utilizing the nature of the for loop. That one for lemma 2. Moving forward to lemma 3. Here's a sample L5 proof idea for lemma 3. We'll use proof by induction to prove that the output list has a size of n factorial for all n greater than or equal to 1. Starting off by proving the base case for n equals to 1, the output will be 1 according to the base case of the algorithm. We'll then come up with an inductive hypothesis of when n equals k, there will be k factorial orderings in the output. In the inductive step, this algorithm uses a for loop traversing through every element while removing the current element before the recursion is called. Therefore, there are k plus 1 element in the output list produced by the current element. By inductive hypothesis, there are k factorial possibilities of extensions for the remaining k positions. By lemma 2, all of these combinations are distinct, giving us k plus 1 times k factorial equals to k plus 1 factorial total possibilities. Again, to receive L5 on the proof idea, you have to provide all key ideas along with a brief description. Making small mistake in the proof idea will lead to an L4. However, anything beyond a small mistake, such as missing key ideas, might result in L3 or even L2. Here's the L3 version of the proof idea for lemma 3. Compared to L5, this version did not justify why you can multiply total possible combinations due to not applying inductive hypothesis, and how the current iteration element is removed before recursion. Here's the L2 or L1 version of the proof idea for lemma 3, where even more detail is missing. This version is not an L0 because it at least provides some correct ideas, such as describing how the k plus 1 factorial possible combinations are generated. Some of you might have noticed that the proof idea for lemma 1 and lemma 2 are pretty similar, and that both the lemmas can actually be combined to one lemma. It can be combined to something like this. Every element in the output list is a distinct ordering of the input list. The second part of the walkthrough video ends here.